Hello everyone. This video I'm going to continue introduce the Newton's laws of motions. And last time we finished the first two law of motion, and this one we just show you the final one, the third law, Newton's third law. Okay, the third law is also give you a lot of stuff. Okay, in original in Newton's book, it said for every action there is an equal but opposite reactions. Okay, that's the very old obsolete language. So in today's world, when you apply a force on if you apply a force on an object, the object also have the force applied on you. Okay, and the magnitude is the same, but the direction is opposite. Okay, equal magnitude. Okay, equal magnitude. That's the important things. Okay, oppositely and equal magnitude. Okay, let's call for action and reaction. Okay, action and reaction, or force and anti-force. Not anti-force. What's the name? It's action and reaction, but it's force and okay, anti-force, react force. Yeah, I just forgot. Okay, so and this the third law is also happening in daily life. Okay, just like I say, you push object, the object also give you a force, push back to you. Okay, the thrust and the rocket use this concept to make a rocket into the space. Okay, the rocket push the gas. Okay, and then also the gas push the rocket. Okay, so and for every day, if you walk, yeah, for every day you walk, when you walk on the ground, you exert a force on the ground, and also the ground also exert force on you. So that's why you can walk, and it's also due to the friction between your shoes and the ground. Okay, so actually friction makes you can walk. Okay, so friction is also very important in daily life. And if you like a dog, yeah, the dog push the rope, but actually also the rope also also pull the dog. Not push. Okay, I used the wrong word. Okay, the dog pull the rope, and at the same time, the rope also pull the dog. Okay, this is equal and opposite. Okay, it's force and it's action pairs. Okay, what's its name? I need to check this out. It's called action pair or it's also called force pairs. In textbook, it's also called action and reaction. They call force pairs. That's the real name? Force pair. Force pair for third law. I remember. Force pair for the third law. Pretty strange. Action and reaction. Force and reforce. No. Action, reaction, and yeah, I forgot the name. Okay, anyway, we just know the concept. That's already enough. Okay, so let's use another example for this action and reaction or third law force pairs. Okay, if there is if you have monitor sitting on the table, if a monitor sitting on the table, and intuitively you will have a. Let me change this. Okay. This one, okay. So you if a monitor sitting on a table, so intuitively there's gravity. Okay, the gravity that's called the weight. Okay, weight. So the weight is the force. Is the weight. The weight is the Earth's exert force on your monitor. So that's why it's written in FEM. FEM. It means the Earth exert a force to monitor. Okay, but this force also has action reaction pair. It's called FME. Okay, and it's in opposite direction with the same amount. This is called monitor to Earth. Okay, that's very counterintuitive. Yeah, this is intuitive. Your monitor sitting on the table. Yeah, you have a weight. Okay, the weight is the earth pulling the monitor down. But at the same time, the monitor also have the monitor also has a force to pull the earth and in opposite direction. But we feel this naturally. But how don't we why didn't you feel this force? Why didn't we feel this force? Because the earth is so heavy. This is so heavy, so that's why we cannot feel it. This is so heavy. So the monitor has the force to pull the earth upward. Yeah, that's true. But the earth is so heavy, so that's why we cannot feel this force. We almost cannot feel this force because the force and like I said, the magnitude of this force is the same as the weight of monitor, and the weight of monitor is so minute, so the force is minute, and you want to pull the heavy earth, yeah, you almost feel nothing. Okay, that's why we feel nothing. Okay, we can difficult to feel. Difficult to feel. Okay, we cannot feel this force. Okay, and then for this system, okay, we also, like I said, we also have four normal forces. Okay, the normal forces, like I said, when you put object on the surface will have the normal force to push you back. Otherwise, the object will keep sinking. Okay, so normal force, and you write T to Tn, that means table to monitor. Table to monitor. And this force also has the action reaction pair, and it's called FMT. The FMT means monitor also has exert a force, also exerts to the table. Yeah, that's very reasonable. You have a normal force push the monitor up, but it has an equal and opposite force from the monitor to the table. Okay, that's why your table, if you put a very heavy object on your table for a very long time, maybe it will have a dent. They show a dent. That's because your object also has a force to the table. Okay, and it's action pair with a normal force. Okay, that's called action, and that's the very simple analysis for this very simple system. And for later, and we will see that. And another thing I have to address is the action and reaction pair. Okay, maybe previous slide shows action pairs, they always act on different objects. Therefore, they can be cancelled to each other. Okay, that's an important concept because maybe in the later we'll show a term called free body diagram. Okay, and in free body diagram we don't show the action and reaction pairs. Yeah, we don't. We in the body diagram, in the free body diagram, we never show the action and reaction pairs, because action and reaction pairs, they act on a different object. They act on different objects, and for most of the time when we draw the free body diagram, we care about a certain object. We want to do the force analysis on an object, on only one object. So the action reaction pair, and action reaction pairs, it acts on different objects. So we really don't care. We never draw the reaction pairs in the free body object. Okay, I will demonstrate later. Okay, for the use a very simple example. Okay, so back to this. So that's why this. So the action reaction pair. So let's use this as an example again. For the weight, it's Earth to monitor, and the reaction is monitor to Earth. You see, this force and reaction, they act on a different object. This is act on the monitor. This act on Earth. And for the normal and for the FTM, FMT, okay, this table has a force on the monitor, and it's monitor on the table. They act on a different object. Okay, so for this system, if you want to draw a free body diagram, especially we want to analyze the monitor. Okay, focus on the monitor. Okay, let's say show this free body diagram for monitor. Okay, so when you want to draw a free body diagram for monitor, we just show this FTM and FEM, because these two force act on the M. Okay, you see these two force act on the monitor. Yeah, here act on monitor. These two force act on the monitor, so that's why we just draw these two force. The other two force, yes, it also has. It also in this system, they also have F, and let's say in this system we also have FME and FMT, but we want to analyze the monitor only. So these two force we won't draw them, because this force act on Earth, nothing to do with monitor, and this force act on the table. Nothing act on table, nothing to do with the monitor, so we didn't draw these two pairs. Oh, but sorry, we don't draw this force on this free body diagram, only show these two. Okay, this is an important concept when you draw later you want to draw the free body diagram. Okay, so that's pretty much about the third law. Let me think, is there many stuff I want to address? This is a very interesting clip for the action and reaction, and you can see by yourself. And for this video, for the final one, I want to address, it's called inertial reference frame. Okay, it's also a very important concept. Like I said, the Newton's law says set up an inertial reference frame. Okay, what's the inertial reference frame? That means the frame is at rest, or as you say, make a note. That's what is inertial frame. It means the frame is at rest or constant velocity. Okay, and a straight line, TRAIGHT, is straight line. Okay, that's if your reference frame, or you say your coordinate is stay at rest or moving constant speed as a straight line. That's called inertial reference frame. Okay, so there's an inertial reference frame, and it also has a non-inertial reference frame. Non-inertial, inertia as inertia. Do we have L? Inertial reference frame. I think as L. Inertial reference frame. Reference frame. Okay, and this video, I think which one? I think is the upper one. I think this one. I remember it's one. And this picture, I think is from this. Is this link? And this is a very great video to show you what's the difference between the inertial frame and non-inertial frame. So I did experiments like there's a ball, and place the ball here, and then the ball, and there's a switch, and the ball will drop. Okay, and he used when we at the rest, you will see the ball go down like a straight line. Okay, and if you sit with the table, okay, this table has a wheel, has tire as a track, okay, and there's a setup here, okay, and then the ball, okay. So let's set up experiment. Okay, set up experiment, and then you can use the same speed with the camera with the same speed as as the the moving as the moving object, and then take a picture. When the camera has the same has a velocity and constant speed velocity straight line, and observe the this free falling phenomenon, you will also constant velocity. When you will see the same phenomenon, the ball drop on a straight line. Okay, because in this system, only the gravitation is the only force. Only has G is only forces. G is only force. Is only force. G is only force. That's why it goes to straight down a straight line. Okay, but let's say it's okay. Let's say I think it's if you have acceleration, if the whole system has acceleration, and if you sit on acceleration frame, okay, if you are in acceleration frame, they make the whole motion of this apparatus has the acceleration to the x direction, and then he take a picture again and show the trajectory is, well, I think it's become like this. Okay, this is the ground. The trajectory will become like this. Okay, if you are in acceleration frame going the direction is right, you will see the trajectory of ball is in this direction. If you're in acceleration frame. Okay, but that's the weird things happen because, like I say, gravity is the only force in this system. Okay, so it should be go down the straight line. Okay, because the direction of gravity is always point downward. Okay, it should be go this way. Okay, but why we observe the trajectory? But this is the trajectory we observe. How to explain this? Okay, because the only force is point downward. There is no other force. So if the trajectory going to left, that means something push the ball to the left. Okay, that's Newton's second law says force cause motion change. So that means something push the ball to the left, because the only force gravitation is only goes downward. So what's caused the ball moving to the left? What's caused the ball moving to the left? Okay, so this is to tell you at least Newton's law only Newton's law. Okay, if you Newton's law only happens in inertial reference frames. That's important concept. Okay, that's why these three laws are all important. The first law looks very simple, but it set up the reference frame. How to set up reference frame at rest, coordinate at rest, or moving at constant speed, a straight line. Otherwise, you are in non-inertial frame. Okay, in non-inertial frame, Newton's law may not be applied. Okay, if you want the Newton's law can be applied, you must be in the inertial frames. Okay, that's very important concept. Okay, Newton's law only happens in inertial reference frames. Okay, so finally, how do we explain this? If you are in a non-inertial frame, and that's why we need there's a term called fictitious force or pseudo force. Okay, something is physics uses a fictitious force, fictitious force, or it's called pseudo force, pseudo force. To explain this, when you are in non-inertial reference frame, you need to use the concept called pseudo force or fixtures force to explain this. Okay, that's important for the inertial reference frame. Okay, that's why the first law is also very important. Okay, that's pretty much about the review the three Newton's law. And the next video, I will show some example for calculate action and reaction pair to show you that's really opposite direction and also has the same magnitude. I will use a very simple example, and I also use a simple example to demonstrate the weight problem when you measure weight in elevator, go up and go down, what's the weight will be. Okay, and I also you demonstrate the action and reaction pairs. Okay, so that's pretty much about this video. So I suggest you watch this video. Okay, it's very old, the 1960, but it's very good introductory video let you know what inertial reference frames are. Okay. Okay, that's pretty much about video, and see you in the next video. Bye bye. Bye bye.